Uh, so before I begin, I'll spend a few minutes reviewing the lecture before spring break. So where we saw what is called the partially observable Markov decision process. So the material that is being covered for today, you can find the references for the material is or if you want a more popular reference, Wikipedia. So I don't think the material that's being covered today is going to be available in the form of notes, so you could refer any of these. So let me just review partially observable Markov decision process. So we have a controlled Markov chain. But we do not have access to the states of the Markov chain directly. But what we have instead is we have something known as the observations process. Which is a noisy function of the states of the Markov chain. So f and g could be linear or non-linear, and the noise sequences. So actually you could think of this as a disturbance to the system, and Wt as being the measurement noise or the sensor noise. So the noise sequences n and W are both IID. And the other assumption is that they are mutually independent of each other. So the goal as always is to minimize the average cost, which we define as a function of the state and the input u. But we have to make decisions, or we have to make our choice for the optimal policy based on the observations, and we don't have access to the states of the Markov chain. So to get over this, we introduced what is known as the belief state, if you remember. So belief state is defined as the probability of the state of the Markov chain being x given the entire history of observations up to the time t. Right, so yt is the all the past observations. But the problem is that Bt by itself does not turn out to be a Markov chain. So further, we augmented the state and formed what we call as the information state. which was defined as a combination of the belief state and the observation process, right? And finally, our goal is to find an optimal policy, ut star, which in this case can be expressed as a function of the information state. Remember this? So what we essentially do is we started with a partially observed Markov decision process, and by constructing this new information state, we transformed it into a fully observed Markov decision process or a controlled Markov chain. And this is nothing but the usual state feedback, where our new state is the information state IT, right? So to begin with, let's look at a simple fully observed system. So case 1, so a special case in a fully observed system is the LQX. The reason why I denote this as X is we don't necessarily need a Gaussian assumption in this case. So this works even if the noise is not Gaussian. So the only assumption is that it's IID and it has zero mean. And has finite variance. So these are the only assumptions that we need as of for this particular case. And because it is an LQX system, so the states evolve in a linear fashion according to this equation. And because we have a quadratic cost, C of XU is C of XU has this form, where it's quadratic in both the states as well as the inputs. And the additional assumption is that Q is positive semi-definite and R is definite, positive definite. So how do you find the optimal policy in this case? Anybody? Sorry? Yeah. So we look at the average cost optimality equation for this particular system. So the ACOE for LQX would be this is the ACOE in a general case, right, for any system. But to do this, we have to come up with a guess for H star. So any guesses for H star? For this, so remember that this is a linear quadratic case. Yes, exactly. So taking H star of x to be of this form is reasonable because it has worked before, right, in one of the homework assignments. The only difference is that in this case we have control as well, u. Probably in the homework assignment you didn't have controls, if I'm right. So you go further and substitute this into the equation. Oh, so do you see an error? Yeah, so there's a P which was missing. So do you see how we got this step? Any questions on this? From this? Okay. So what do you do to find the optimal policy now? Anybody? Sorry? Yeah, take the gradient with respect to u, right? Because we have a minimum over all possible u's. This thing within the brackets has to be the right hand side. So the step, so to solve this, we need to take the gradient of this whole thing within brackets with respect to u, right? So the gradient of this let's call this equation star. So taking the gradient of equation star with respect to u, you get So do you see how we got this? Is this okay? So now we can simplify the expectations and find the optimal U star. Yeah, this is 0, so this term goes away. So you're left with an equation that is u and x. And taking terms together, you would so you end up with this. So this is your optimal policy. So what you have here is an optimal policy is in the familiar form of a gain term multiplied by the state, right? Which is the same as your state feedback. So do you see why we didn't have to assume Gaussian in this case? Do you see why? Because so if you remember, I called LQX, not LQG, right? Right. So do you see why we didn't require a Gaussian assumption? Yes, and finally the sorry?
Zero mean. I mean, you would even have to be zero.
Yeah, it didn't necessarily have to be zero mean. Zero mean was taken just for simplification,
Okay.
like simplifying it.
You just gotta know it. All right.
So we just needed IID.
Yeah, quick question.
Yes.
On the figure right here, we have RU. At what point do we just call it U star?
U star.
U star at the next
So
is that already U star one?
yeah, this is already U star. To be precise, this is U star because you're equating it to 0. So at this point, I wrote the gradient of this with respect to U evaluated at U is equal to U star is 0. So in this step, I can, yeah, that's right. Yeah, the thing I wanted to stress is that U star is independent of the noise statistics. So it doesn't really depend on the noise statistics. So that's why we could get away with an LQX system instead of an LQG system.
But if it was not zero mean, what expect to it mean? If it was not zero mean?
Oh, if it was not zero mean, I might have to think about it. If it was not zero mean, you said, right?
You will get a B. So you get
Oh, you would have, yeah.
H star times whatever the mean of n.
So you would have cross terms where you would have expectation of n, and if that doesn't turn out to be 0, but then did you really?
You end up getting an extra constant. Right?
Yeah, that's all
The part that you erased.
Here?
Yeah, because remember there was the
You have an r
B transpose.
Because,
times the
yeah. You have this B transpose H star expectation of n.
Yeah.
That's the only thing that comes. Correct. Yeah.
Here we're assuming that you can observe all the states. This LQ.
Yeah, this is a fully observed system. Just to emphasize that, I mean, this can be carried over to the partially observed system as well. That's why I wanted to consider a fully observed system first. For a simple LQX system which has linear state evolution and quadratic costs, you have a nice formula for the optimal policy.
I have one question. Where does the assumption, so at the beginning you made an assumption, IID in the spine has 0 mean, that the second moment, so you said the second moment is finite?
Yes.
N-square is finite?
Yes.
Where does that assumption come into play here?
Where does that assumption come into play?
Like why are we, like, do we even need to make that assumption? Is that necessary here?
I have to think about it. I can't get that.
Because there were some steps that we skipped going from the min to the gradient. Because you have to expand out.
Yeah, like the min you would
This?
get an n square in there for sure. That's true.
So the reason why you need that assumption, the finite variance, is you still haven't found what your eta star is. So eta star, if you look at this equation, would be, so if you
Okay, I see.
if you remove all the terms with x and u and just look at the constant term, that would have an expectation of n squared. I mean, n, yeah.
We need that.
Yes.
So I think you extend the gradient expectation over there, and for that I think we need like when I took the gradient
Yes.
over there,
Right here, right?
that's the expectation,
Okay.
and I think we do that.
Maybe. Not quite sure.
Yeah, you need the expectation to be finite to take the gradient.
Well,
An expectation
I'm
is
not
an
sure.
integration.
I'm not sure if that's true because you're taking the gradient with respect to u, and so the expected value will just go and append itself onto the end. And so then, like u is deterministic, so then you can just pull that outside.
Yeah, I'm not sure if that's right, but what the main reason why we need the finite variance assumption is eta star is going to be, if you want me to write it, if you ignore all the terms with x and u and just look at the constant term, you would have expectation of n transpose H star n, and that's what your eta star is going to be, right? Is that right? Yeah. So this.
What we choose for H star, or
Yeah, H star. So yeah, that's the next thing I wanted to get to. So how do you find H star?
ask a non.
So now you have an expression for U star, right? U star. So plug this back into your. So I don't want to write that out, but I just wanted to mention it, that if you plug,
Okay, I see. Yeah.
if you plug this back into your original ACOE,
Just a giant quadratic.
yes, and that's what is known as the algebraic Riccati equation. So H star solves the Any questions? Any other questions? So at this point, we have a closed form solution for the optimal policy for an LQX system, or for a fully observed LQX system, right? So now we want to move to a partially observed system. Yes?
Talk about the LQR system in the first, like how's that different from LQX when he says an LQR?
LQR. Yeah, there's no noise in the LQR. Was that already covered, or is that?
Wait, yeah, that was like in the beginning. I remember.
Oh, okay.
Something. It's
Okay.
kind of similar, but
Okay.
okay, so no noise.
Yeah.
That's not too much different.
Can you give us a quick little primer on these acronyms? So LQ is always linear quadratic,
Yes.
and then G is Gaussian.
Yes. Yes. That's right.
R is,
R is regulator, right? LQR. R stands for regulator. Sorry?
so that means no noise, or the R?
Yes. Yeah. LQR is. I think it's used in the context of deterministic systems. Probably it carries over to, because finally you see that if you make that zero mean assumption, the optimal policy doesn't really depend on the noise. It's just usual state feedback, right? So I think it can still be used in the context of LQX. I'm not sure though. Like you would want.
X, what's the X?
LQX is because X needn't be Gaussian. Anything other than, I mean, yeah, we don't need that assumption. It could be Gaussian, but we don't really need it. Yeah.
Usually it's LQG, G's capacity.
Okay, so LQG would be like a subset.
Yeah. True. So in this, for the partially observed Markov decision process, we make that additional assumption of it being Gaussian. So the state evolution is the same. And you have observations as well, right? Noisy observations. And so NT is distributed as a Gaussian with zero mean and covariance sigma n. W is again another Gaussian with zero mean and covariance sigma W. And we assume that N and W are mutually independent. So Gaussian is special in this case because the belief state for this particular system it turns out to be Gaussian. And that is advantageous because for a Gaussian distribution, you can characterize it using just the mean and the variance, right? So earlier belief state was a vector in dimension d, where d is the dimension of the states. So for this particular LQG case, belief state can be characterized with just the conditional mean and the covariance. That's the property of a linear Gaussian system like this. So what is going to be the optimal estimate in this case for a linear Gaussian system? Same as in?
Same as the observed case?
The observed case. No, in the observed case, we didn't need an estimate, right? Because we have access to the Markov chain. So we didn't really need an estimate. So in this case, so this is your controlled Markov chain, but you only have access to the observations. So based on the entire history of observations, you want to come up with an estimate of the state. So what I've given to you is that the belief state in this case is going to be Gaussian with so this is the x hat t is the conditional mean, and sigma t is the state covariance. So how would you get the optimal estimate is my question. Yes. Yes.
You observe a y.
Yeah.
The belief state is the probability.
You observe all the y's.
Or you observe.
You remember all-
That's why you have a script y here, and not just y. Yeah.
Times
Yes.
and then and is it the probability of the maximum probability?
No, it's the so
See, it's
so
a PDF.
yeah, it's a PMF. It's a PMF. Yeah.
So you're, like, for the rover, just end up saying like, well, I saw, I'm on the hill, I'm on the hill. So with probability 0.9, I think I'm not on the hill. With probability 0.9, I think I am on something like that.
So it's a whole PMF.
Yeah, it's a whole PMF. So usually it's it is a vector of d dimensions, where d is the state space of the Markov chain. But in this particular case, if you know the conditional mean and the covariance, you pretty much know. For a Gaussian system, you just need to know these two quantities, right? So that's the idea. And so the optimal estimate in this case is given by Kalman filter. So I don't plan on doing the derivation of the Kalman filter, but I'll give you the expression for. So it's probably, is there a question? Yeah. So I think it's probably better if I write it side by side so that So the two things that you're interested in, the conditional mean and the covariance, right? And Kalman filter gives you an iterative expression for both. So you can see that, so the dynamics of the conditional mean remains almost the same as the dynamics of the actual Markov chain, right? You have the same A, you have the same B, and you have the same control input ut. So the main difference is that instead of nt plus 1, you have an nt plus 1 hat. So nt plus 1 hat is this. So this is the form that a Kalman filter takes. So LT here is what you call the Kalman gain. And yt minus yt hat. So yt hat is yt hat is the estimate of the observations based on the estimates of your state. And yt minus yt hat is known as the innovations process. So what you need now is an expression, an iterative update equation for the covariance, right? So it's actually a complicated expression which is not of much interest to us right now. So I'll just write it down as this. So the state covariance at time t plus 1 can be written as a function of the covariance at time t. So where G has a particular form which I don't plan on writing. You can easily obtain that in Wikipedia. So now we want an expression for LT, right? Which is the Kalman gain, the gain that you have to apply at each time instant for you to get the best state estimate. So shall I erase this? So Kalman gain can be expressed in terms of the covariance, and C is something that we know, and you know what the covariance of the measurement noise is. So this can be computed. So now it's complete, right? So you have an iterative expression for the mean, which is the state estimate. In terms of LT, you have an expression for LT which you can plug in, and then you also have an update equation for the covariance, right? And if you keep running this for all time t, you can get the best estimate of the state of the Markov chain, right? Correct? Any questions? So what remains to be seen is, so now that you have the best state estimate, how do you get the best policy? Or how do you, so in the previous case, in the fully observed case, we saw that you had a nice closed form expression for the optimal policy in terms of the state, right? So in this case, so now you have a partially observed system, right? And not a fully observed system. So in the general case of a partially observed system, the optimal policy is a function of the information state, right? But in this case, in the LQG system, BT is just these two. This and this. BT can be fully characterized by these two. So, so what I would like to show now is, so in the case of an LQG system, it simplifies further. So you don't really have to have all this information to get the optimal policy. That's what I would like to show you. So for that, so what is it that we are trying to minimize? So we are trying to minimize the average cost, right? Which is the expectation of C This is the quantity that we are trying to minimize, correct? And so our cost is quadratic, and so it becomes this, okay? So now writing this in terms of your state estimate, x hat t, is this fine? Is this, can you understand this, the last line? Does that look fine? How we got this from this? So we just added and subtracted, right? So the difference between xt and xt hat is xt tilde, that we denote it as xt tilde. So we have xt hat plus xt minus xt hat. So if you add these two terms together, you get this, right?
The estimate plus the error.
The estimate plus the error, yes, yes. So what happens now is I think I need the expression for xt and xt hat side by side so you can see it. So what are you trying to minimize it with respect to? You're trying to minimize it with respect to ut, right? Your choice of ut. And so the second term over here, if you plug in these two equations for xt and xt hat, so the ut terms cancel out because you have dut here and a but here, right? So they cancel out. So what remains is just an expression in terms of just x. So the second term here, this is independent of ut. Right? So essentially you can just take this term away. I mean, as far as optimization goes, you don't need to consider it. So minimizing this, the second line, is the same as minimizing the first term of this line. You can forget about the second term because that doesn't involve ut. And from the previous discussion, the fully observed LQX system, you would remember that for something that looks like this, the optimal policy was this, right? So you just have to extend that to this. So it's the same as, so we have already shown the equivalence of optimizing this with just the first term. So you can just replace it with the x hat, which is your best state estimate. So now you have a nice form for the optimal policy for an LQG system. Even though it was partially observed, you don't really need any of this. So you don't need the information state and any of that. So all you need is just state feedback with the estimate of the state. Any questions? I think, yeah, that's pretty much it for today. We've run out of time as well, I think.
So in this case, you just feed your state information or your estimate into your typical policy, for these systems,
Yes.
you don't have to develop some new controller. You're just like, hey, here's my estimate.
Yeah, because Kalman filter gives you the best estimate of the state, and then you use that in your state feedback, and that's the best policy that you can get. And this is true only in the case of LQG. This is why the Gaussian assumption is also essential, because if you don't have the Gaussian assumption, you don't have, the Kalman filter is not the optimal filter. That's it.